welcome everyone. Just wanted to say welcome back, and hope everyone's got a seat here. I think we've got another table over there. First off, I'll just introduce the Board of Governors and Executive. So first off, we've got Jacob Huff from Governor, Richard Cameron, Governor, Chris Rowley, Governor, Adrian Matani, Governor, Adam Moons, Governor, and then Aaron Dobson, our Secretary, Chris Fudge, Treasurer, Dan Redmond, President-elect, and I don't see Abby here. I think no Abby Saunders, our past President, and then I'm Adam Graham, President. So hello everyone, and welcome to the guests. Next up, Aaron's going to come up and read off the guest list, and welcome you guys here.
All right. So lots of new faces here today, lots of guests. So I'd like to welcome Luke Sharon, Bin Jong, Stephen Menke, Martin Theoret, Brent Follis, Richard Levesque, Ryan Racine, Husan Halimi, Eric Hilkeast, Andrew Nadar, Luke Pellerin, Byron Paulson, Michael Callahan, Hunter Davis, Songjin Huan, and Gurbinder Sandhu. Thank you.
Thanks, Aaron. And thanks everyone for coming out. Next up, I'll get Celine Baribeau come up and talk about new members and membership.
So the new members that joined our chapter since our last meeting are Tarek Abouimara, Pierre Desjardins, Dent Harrison, Rebecca Pinto, Araz Ashuri, Xiao Shi, Geoffran Chiha, Darcy Gray, and Christopher Goody. So welcome to the Ottawa-Valley chapter. I would also like to congratulate Ryan Dickinson and Nicholas Lee on their membership advancement from associate to member. Congrats.
Next up, I'll get Adrian up here to talk about the ASHRAE Career Fair happening next month.
Hi everyone, I just want to talk about the career fair that we have at Carleton. It's at the Fen Lounge again, same as last year. And we have a great group of students that are coming out from Carleton, Algonquin, as well as Ottawa U. We're also going to be reaching out to La Cité and some of the other and Cégep Loudoun. If you are still interested, the booths are open for registration until Friday. So if you have any questions, please contact me, or you can go online to the OVC website and you can register there. It's $200 for a booth and $100 for sponsorship. We have a really great set of booths this year, but we'd love to have some more, so please do go online or contact me if you have any other questions. Thanks very much.
Thanks, Adrian, and thank you for setting up the career fair again. It's a lot of work goes into it, and it's been very well attended the last few years, so thank you very much. Next up, I'll get Peter Shawwood to come and talk about some of the things we're doing in student activities.
Yeah, so just a follow-up from last month's announcement. I had Kevin Cornier volunteer his time to help out the students at Carleton and New Ottawa for that joint student entry, which is great. Seeing a lot of positivity out of that, so big thanks to Kevin. I don't think he's here tonight, but certainly appreciate it. That's it for me, but I'll see you guys at the career fair.
And Joe Delaval, all right, he'll talk to you about gay.
Hi everybody. Two announcements to make. One would be related to congratulate James from Long Hill on winning the axe throwing last 2 weeks ago. It was a great night out by all. We had about 18 people out there. And I'd like to thank all of you for who did come out. James, I'll get you next year, buddy. And the other would be the Board of Governors has selected Celine to attend the YEA event, Leadership Weekend in Seattle, I think it's the 3rd week of March. So I'd like to congratulate her on that and hope you have a great time there. I'm sure you'll make the most of it. It's a really good experience. The last thing would be, I think we'll probably have another event at the end of March. So probably tailgaters for pool and just a more relaxing event, no axes thrown around. Thank you very much.
And next up, I'll just run through a few things for Colleen for our ASHRAE curling event next month. We're hosting it on March 9th at the Nepean Sportsplex. So if you haven't signed up, there are still some registrations available. Cost is $400 a team. It includes curling and dinner, and I'm sure some fun on the way. And since 2010, we've managed to raise about $12,630 towards either the ASHRAE scholarship or some local causes or Haiti relief. There's been a few great causes that Chris Ely kind of started on. So hopefully we can continue to do that every year and invite you all to sign up. So thank you guys. Next up, I'll get Dan Redmond to come up and give us a quick RP update and maybe talk about those tickets he's selling for something.
Yes, tickets. Hi everybody, my name is Daniel Redmond. As Adam said earlier, I'm the president-elect of the Ottawa chapter, and I'm also the RP chair this year. So one of my duties is to solicit money from people. And it's not just for me, sorry. It's actually for ASHRAE research promotion, and it's something that is near and dear to the hearts of everybody in this room. This is the mechanism by which ASHRAE gets funding to further development in codes and standards. Again, every dollar raised in Canada goes towards research in Canada, and typically, for every dollar invested, we're able to put $2 to $3 into active research here in Canada. So tonight, I'm raffling tickets. There are 4 tickets to see the Ottawa Senators face off against the Buffalo Sabres on Thursday, March the 8th, with a parking pass. The seats are in section 109, row C. So when I think of the alphabet, I think that's pretty close to the S. So they're fantastic tickets with a parking pass. If you haven't donated yet, please, and you're interested to do so, please raise your hand and I will come find you. Later on in the program, we will be raffling tickets and see who the winner is. Thank you.
Thanks, Dan. And thank you everyone who's continued to donate to ASHRAE research and hit up every time they come in. So thank you. Next up, I'll just give you a quick update from the winter meeting. We have a couple of exciting developments. One of them being Jeff Clark being nominated as Region 2 DRC. That's a great thing to see, someone from our region moving up in the society world. And then another very exciting one with a local person here, Daryl Boyce, being nominated as the president-elect for all of society. So that'll be starting in July of this year. And definitely a big accomplishment for Daryl. So I want to congratulate both of them on those nominations. So I think everyone, give them a round of applause. And next I'll call up Jacob to talk about CTTC.
Hey everyone. So another development from the Winter Conference was the Technology Award. So we actually had a winner for a Technology Award here in Region 2. So it was the Mountain Equipment Co-op from Pajot-Morel in Montreal. And to that note, I want to let you guys know that we are accepting invites for this year's Technology Awards. So the deadline is March 23rd. So there's a number of different applications that you can take. So there's commercial, institutional, healthcare, industrial, public assembly, or residential. All of which there's a separate award for a new building, an existing, or a retro commissioning. And we're looking for any sort of project that you might be proud of or that shows efficiency or any kind of innovation. If you've got any questions, just let me know, or frankly, anybody at Total HVAC, they'll be able to help you out.
And thanks to everyone who's submitted tech award applications in the past and continues to do so. I don't think we get enough. We've got a lot of great buildings being built in Ottawa, a lot of great designs. Encourage you to submit those, even if it's just to the chapter level or region. Pretty quick form, send it off, get some recognition for your great projects. Next up, we'll just take a quick break and we'll have some dinner, and then we'll reconvene. We'll do the RP raffle, and then we'll get to hear our distinguished lecturer talk to us a bit about Seismic. So there are two tabletops. So I'll get a representative from each of the tabletops to come up and just do a quick blurb on the product. So I guess Adam, we've got Masters representing that.
I knew he was going to get to it eventually. So, my name is Adam Moons. I'm with the Master Group. I'm here representing NAD Climate tonight. Comprehensive line of air diffusion and distribution technologies. If you have any questions at all, feel free to give me a call or stop by our table at the end of the evening. I'm going to be around for a while afterwards to answer any questions you might have. Thanks.
Next, go ahead, Richard Levesque from HDS. Talking
Good evening, Richard Charlavec, HDS Engineering. You probably all heard of me at some point, sorry not me, but HDS. And myself, maybe some I step on a few things. So we're here tonight with the new lines that we have now, the newer line, vibroacoustics for seismic restraint, vibration isolation. Which is this one I have right now. We also have acoustical products, but anyway, if you have any questions, I'll be over there later. Thanks, guys.
Thanks to everyone who continues to rent out the tables and support the chapter through some advertisement and raising a bit of money for the chapter. So thank you, everyone, and now we'll start seating for dinner, and we'll reconvene shortly. Thanks. Hello, everyone. Just figure while we're eating a little dessert and getting some coffee served, we'll start and do the raffle. So I'll get Dan to come up and do that, and then shortly we'll get started on the evening program.
Thank you very much, Adam. So if anybody still hasn't donated, your chance is very soon going to be. The tickets tonight were donated very graciously from the Master Group, so thank you very much, Master Group. And I'd actually like to ask our speaker to draw the lucky number. Thank you. So it's a blue and white ticket.
2 inches
Number 9, 8, 6, 8, 5, 8, 5.
Could you repeat that number?
85. Draw it.
So I have 85.
Redraw.
That's it. Way to go.
Oh, Mr. Raleigh.
Yeah, you better check that out.
No, it checks out. Thank you very much, Chris.
And also to Group Master, that's very good of you to do the donation. Thanks again. to try the raffle? Because that's twice this year. It's pretty good odds.
So with this raffle, that brings us to, as part of our annual campaign, right now we will be roughly 57, 58% of the way complete, 56 with the raffle. With the raffle, we've now raised about $16,500 towards our goal of $30,100. Thank you very much, and please, we appreciate your generosity, and please continue your support. Thank you. $600.
Raised.
Thank you.
Thanks, Dan. Thanks, Masters, and congrats, Chris. So next up, I'll go through and introduce our speaker here. So the program tonight is Seismic Restraint of Mechanical Systems, something most of you are likely familiar with here in Ottawa. So the lecture goes over how mechanical systems are seismically braced, includes piping, ductwork, suspended equipment, floor supported equipment. Other topics discussed are housekeeping pads, building codes, anchorage and specifications. Typical details from the ASHRAE manual, a practical guide to seismic restraint will be reviewed. So the speaker tonight is a distinguished lecturer from ASHRAE Society, Mr. James Tauby. He's the Chief Executive Engineer for Mason Industries, a worldwide leader in the field of noise and vibration control products, as well as seismic and wind restraints. He's a professional engineer in 45 states, holds a Bachelor of Science in Mechanical Engineering from the University of Alabama. Regularly lectures around the world on topics ranging from vibration isolation, seismic and wind restraint of mechanical systems, to the use of elastomeric expansion joints for piping in seismic applications. He's a member of a team of engineers that inspected numerous buildings after the Loma Prieta and Northridge earthquakes. He's been a featured speaker at the American Society of Plumbing Engineers and ASHRAE National Conventions numerous times. Past chairman of ASHRAE Technical Committee TC 2.7, Seismic Wind Restraint Design. He's currently the chairman of ASHRAE Standards Committee SPC 171P, method test of seismic restraints for HVAC equipment. He is currently ASHRAE's liaison to the American Society of Civil Engineers, Wind Load Task Group. He is a member of ASHRAE Standards Committee, member of the Hanging Bracing Water-Based Fire Protection Systems Technical Committee for National Fire Protection Association, and a corresponding member of the Building Seismic Safety Council, TS-5, Masonry Construction. Member of the ESSC Anchorage Task Group, editor on FEMA documents 412, 13, 14, for the installation of seismic restraint on equipment, piping, ductwork, and electrical distribution systems. Lead author of an ASHRAE design publication, A Practical Guide to Seismic Restraint. This includes code requirements, specification considerations, seismic restraint, connection methods, along with determining whether a piece of outdoor equipment is governed by seismic or wind loads on a particular project. So quite the resume here. And without further ado, I'll invite James up to speak to you guys about seismic. Thank you.
Wow, nobody usually goes through all of that. They usually get somewhere along and they stop and go, that's enough, and then go on to the next slide, okay? Thanks for having me here, all right? When I saw your director at large back in Chicago a couple months back, he told me I was stupid for coming up here with only a 1 day's notice. In other words, I was planning on flying up this morning and having the show tonight, and he's like, no, you gotta give yourself at least 2 to 3 days because the weather's gonna change and you're not gonna be able to get there. Well, it worked out pretty good. It got pretty warm and I was able to get here today. So today we're gonna talk about some seismic restraints and mechanical systems. What I'm going to show you is a lot of photographs of things that did not work well during earthquakes and what the fixes are. Right? Everything I'm going to be going over. Right? We'll get rid of some of the ASHRAE stuff first. All right. ASHRAE is always looking for help, and they're always looking for people to take a look at what the distinguished lecturer system is doing. So they're asking you to critique what I'm doing here. All right, up until about a year ago, most everyone was, they handed out a form and you filled it out, so on and so forth. Well, now it's all done electronically. So basically, there is a place to go online and say, yes, he did a good job, no, he did a bad job, he was too commercial, he had too much commercialism, so on and so forth. All right. ASHRAE is looking for this. ASHRAE needs this. There are a lot of people that look at some of the ASHRAE distinguished lectures and they're not particularly sure that they want them to still be lectures. So this is how we kind of weed out the people that maybe shouldn't be doing this. Okay? Volunteers. Okay. ASHRAE is always looking for volunteers. I have been a member of ASHRAE since my sophomore year at college in 1978. So I've been in ASHRAE for 40 years already. Okay? I still don't get a discount because I'm not old enough yet. A few more years and I'll get a discount. Okay? But ASHRAE is always looking for volunteers. They're always looking for help. And it's at every single level. All right? I found the easiest way is to just jump into a TC and become the dreaded secretary of the TC. Nobody wants to be the secretary because it's stigma of being the secretary. But let me tell you, it's probably the best position to get to learn the people that you're dealing with. When you're a secretary, you're taking all the notes, you're taking down everything that's going on, and then you're remunerating it to everybody else in the place. You're going to meet everybody in your TC when you do things like that. And that's what I've been telling people for years. Take the secretary job. Nobody will want it, okay? And then what usually happens in most TCs, you go secretary, you go membership chair, you go vice chair, and guess what? 4 or 5 years later, you're the chair of that committee, okay? By then, hopefully you've met everybody, you're doing well, and you can go ahead and take care of the chair position, okay? Needed for everything, all right? We need people at this level here and at the meetings, all right? If your company is willing to send you to the ASHRAE meetings around the country, all right? That's great, all right? But you got to join and do something with it, all right? I start Friday afternoons is when I have to go to the ASHRAE meeting, and I don't leave till Thursdays. I'm a member of TAC, which means I am on the Technical Activities Committee, and I take care of all the TCs in the refrigeration section, which is section 10. All right? So I'm their liaison between ASHRAE. So anything that they have questions on, how should they go about doing this or that, comes through me. I get it from ASHRAE. If I don't know the answer right, and we go back and forth. And it's a way of keeping everybody involved. Okay. All right, this is worth 1 PDH from the American Institute of Architects, okay? All right, this talk is by ASHRAE. ASHRAE has a contract with AIA to go ahead and give out PDHs, all right, for the different talks that we have, okay? All right, so this goes over how we're going to go over mechanical systems, all right? Going to go over some building code, a little bit of specifications, and I'm going to go over housekeeping pads. And you're sitting there going, who cares about housekeeping pads? Wait till you see some of the photographs of these housekeeping pads. It's probably one of the more important parts of the mechanical room itself is the housekeeping pad. Okay? We're going to go over different types of bracing. We're going to go over some testing. All right? And we're going to show some videos of testing of shaker table testing of equipment. Okay? ASHRAE is registered with the AIA, which I just went over. Okay? Everything I'm going to go over is in this manual. It's a practical guide to seismic restraint. It is the second edition. The first edition came out in 1999. The second edition in 2015. All right? Between 1999 and 2015, I was able to add another 100 pages worth of information, documentation, and design work. Okay? It is part of the United States Building Code. It is part of many of the building codes as a reference document around the world. Right? If you go to Australia and or New Zealand, it pretty much says this is how we want you to do as per this book. Okay? Now we'll go over the objectives. All right, we're going to go over some specifications, building codes, connection types, housekeeping pads, braces, floor mounted equipment, suspended equipment, and testing. Most of this is requirements of the EIA that I have all these slides. All right, otherwise I talk over the same thing many times over, okay? Specifications. It's probably the most important thing you can take away from this talk tonight, all right? Without a specification, all you got is a hope and prayer that you're going to get it done the way you want it done, all right? Without a specification, what you're going to get is whatever is going to be the cheapest, or if you don't specify you physically got to have something, you're not going to even get it, all right? Codes many years ago used to say, add seismic restraints. Wow, that's a great term. What does that mean? Does that mean I just put a bolt in it and walk away? Or does that mean I have a cable system? You know, without a specification detailing exactly what you're looking for, you have no idea what you're going to get, if you're going to get anything at all. Right? So it requires a properly prepared set of construction drawings, right? Drawing specs, detailed review, approval of shop, and this is probably the biggest problem. Field enforcement. You would not believe how many times I ship materials to a job site. Give them everything. Give them the bolts, everything. And you get to the job site and it's not installed. Or it's installed with something other than what you gave them. Why did you install that bolt versus the bolt I gave you? Oh, because you gave us a 5/8 bolt with a 5-inch embedment. I put a 1/4-inch bolt with a 2-inch embedment. It was a lot quicker. Well, obviously, a 1/4-inch bolt is not going to handle the loads that we had designed for 5/8 bolt. And you see this all the time. Or you'll get people that, it was supposed to be a bolt that was supposed to be embedded 6-7 inches. They cut 3 inches off and stick it in because they didn't want to drill that far down. All right? And that's not uncommon. It's actually fairly common with a lot of contractors on the low end scale. They'll do anything to try and save another hour or two. Okay? Seismic restraints need to be looked at as an engineered system and not a bunch of catalog parts. In other words, you just can't open a catalog and say, all right, send me 10 of these, 5 of this, and 7 of that. Okay? You need to have calculations saying, okay, you need a brace that can handle X amount of load. All right? You're not going to find that in the catalog because somebody has to do the calculations. All right? So you have to have a complete load path. All right, from the equipment to the structure must be taken into account. And that's what I'm going to talk to you about when we get to the housekeeping pads. All right, load path, equipment, bolting to whatever, down into the structure itself. All of that has to be taken into account. Okay, this is the U.S. Building Code, slightly different than the CNBC. All right, when it gets to the end, basically you're going to have about the same values. I'm going to skip this. Connection types, all right, bolts, okay? The easiest thing to do is design for the lowest category of bolt available to the contractor, and that is basically an A307 bolt, all right? But the bolt has to be designed to handle the shear and vertical forces. If you design for an A307 half-inch bolt, okay, you say, all right, in your calculation you said to them, and it says A307 bolt, that's fine. That is basically that's the lowest quality bolt you can buy. So that's going to be anything he can buy at any hardware store, any of his distributors. If I was to say, oh, it needs an A325 bolt, well, that's a structural bolt. That's the ones that they actually bolt buildings together with. Now, what are the chances that the mechanical contractor is going to have an A325 bolt in his gang box? Chances are none. So he's going to put in a half-inch bolt. Maybe not even realizing that there's a difference. And now all of a sudden, instead of having the bolt that you designed for, you got one of an inferior quality. So the best thing to do is actually design for the lowest quality bolt, and then anything you get is either that or higher, which is fine. To put a high-strength bolt in place of that, perfectly fine. Go the opposite way, absolutely wrong. Here's what happens when you don't have good connections. Okay? All these photographs were taken by myself or a couple other people during the Northridge earthquake of 1994. Okay? So what you got here is a cooling tower up on the roof. Okay? Hey, the connection down here is great. They got a big concrete pier. They got bolts sticking out. The bottom of that I-beam is perfect. But the rest of it didn't look so good. What happened was this connection right here got 2 big bolts. All they did is tack weld it. it together. So it really didn't have any strength. And as soon as the earthquake hit, it rolled the one way, these two tacks broke, and the only thing holding this cooling tower in place is the vibration isolator. All right, it's damaged, obviously, but it's still holding everything together, okay? That was not one of mine isolators. I don't know whose that is, okay? So then you have, what is installed, most of it is post-installed anchors, and that is into concrete, okay? Post-installed anchors include wedge, undercut, and adhesive anchors, all right? They have to be tested to AC 355.2 or the European equivalent, all right, to ensure seismic capability, okay? That is the greatest thing in the world except for one thing. In the United States, the mechanical codes say absolutely nothing. They say everything, all the equipment has to be braced, but the rod that holds up the piping or anything else doesn't have to abide by this. So what you have is all the seismic braces have got seismic capable bolts, and then the equipment, the rod that physically holds everything up is not a seismically rated anchor. And in most cases in the United States, it's a, what we call a drop-in. They're basically a nice cheap little anchor. He can push that up into there, and he can thread a threaded rod into it, and he walks away, okay? And then you have wood types, all right? Probably more towards the Vancouver area, in BC, all right? They still do a lot of buildings designed out of wood, and you'll need to lag bolt into those, all right? The National Design Specification is a great little manual for designing wood construction. So what you've got is they'll tell you exactly a 3/8 by 4-inch lag bolt that's got a hole drilled of a certain diameter into this species of wood with this amount of water still left in it, gives you a load of this. It's a great little manual, okay? And it goes over and explains how, and one of the main things is it tells you the right size drill to use. Because I've seen too many guys go, okay, it's a 3/8 anchor, I'm going to drill a 3/8 hole. It kind of don't work that way, okay? Housekeeping pads. All right, it's probably the most overlooked portion, and nobody thinks about it, okay? Up until 1994, when I saw the housekeeping pads shattered, and I'll show you pictures in a moment, we didn't think about housekeeping pads. We said, okay, we have a piece of equipment, we'll say it's a pump, we're mounting it on a housekeeping pad, we just build a housekeeping pad. And how is a housekeeping pad built? All right? You've got the structural floor, we're going to put it right where this is here. So we form up some wood around it, make up some concrete, dump it in place, that's it. About a week later, they come back, they strip the forms, and maybe another couple, 3 weeks after that, the equipment goes on top of it, okay? But all you've done is you've added weight on top of the structural slab. There's no doweling to the slab below, and there's no reinforcing in the housekeeping pad itself. So all you've done is made this big weight of useless concrete, okay? But it was done by everybody. I mean, even California, all structural engineers, that's the way it was done. Nobody thought about it. And then what happens is this, okay? Housekeeping pads shatter into a million little pieces, right? Here's the seismic restraints. Oh, they're still physically attached to parts of the concrete slab, but not to the equipment anymore. This photograph was a hospital. This was a mechanical room on the 3rd floor of the hospital. And what they had was basically a seismic sensor on that 3rd floor. This floor saw a 1.1 vertical G input. So the assumption is, earthquake came, the equipment got pushed up in the air, and since this was not attached to the structural slab, but it was attached through these seismic restraints to the chiller itself, it went up with the chiller, came back down, shattered like a pane of glass, going every direction humanly possible, all right? So then what happens? Well, what you don't ever want to happen. All of these connections break. And where does that water go? Anywhere it wants. And gravity takes it down. So what happens is, you're on the 3rd floor. Everything below the 3rd floor gets wasted, okay? Water hits this ceiling, takes out the ceiling, takes out the walls, takes out the floor, goes to the next one down, and it takes out the equipment that's on this floor, okay? It is one of the worst problems that you can have in the mechanical world is when you have a failure at an earthquake. 70% of the monetary damage to buildings in Northridge were caused by mechanical failures. It wasn't structural problems, it was mechanical failure problems. A lot of buildings were just knocked down because it was cheaper to knock the building down and start over than to try and fix all of this. Here's the back side of the equipment, all right? Part of the slab is still fine, still attached to the unit, but some of it is still like, there's one of the restraints out there, there's another one. They're just out there in the middle of nowhere doing nothing anymore, all right? So housekeeping pads need to be reinforced and they need to be doweled to the slab below. In the ASHRAE manual, we've gone ahead and we have figured out what that doweling and that reinforcement needs to be for all different kinds of. This is typically what it looks like, right? This is what you should basically have: reinforcing and some kind of dowel down into the structural slab. So at ASHRAE, we've gone ahead and we've put together this set of charts for different seismic zones. And say, okay, if you've got a piece of equipment and the housekeeping pad, the combined weight is X, okay? And it's up to this many square meters. This is all you need. Number 3 rebar with perimeter doweling at 5/8 and the interior doweling. Now, interior and exterior doweling are different for one reason, all right? Under the middle of the housekeeping pad of the chiller, you got nothing going on here. But at the edges, that's where you're going to have your attachments. That's where you're going to be putting your seismic restraints and things along that line. So the doweling on the outside is heavier than the doweling on the inside to take care of the seismic uplift problems on the outsides. But there were a few other problems that we also found at the earthquake, okay? Edge distances, okay? Basically, it used to be 6 diameters. That was the old anchor bolts used to be 6 diameters. So if you had a 1/2-inch bolt, you had to be 3 inches away, okay? Well, if you're 3 inches away, which is kind of like, it was right here. This one was right here, and the second one, there was one here. So one was here and one was there. When the earthquake came and knocked that edge of the concrete off, this anchor is now out in space doing nothing. This one couldn't handle the load and sheared off, okay? A little better view is this one here. Same kind of thing. Got a big seismic restraint, big, nice, big seismic restraint, some kind of concrete pad, all right? Probably for a pump base or something like that. And when the earthquake came, it went to the left, and it just knocked that whole edge of the concrete off. And there's the 2 anchors. They're still in there. They're just hanging out in space doing absolutely nothing. So the code of the United States, the ACI 355 and 318, now require a minimum of 1 bar between the outside and the first bolt. So you must have an anchor, you must have rebar outside now to keep the edge from being knocked off. Plus you're in farther than you used to be. Okay? Then typically this is what it looks like. All right? Suspended piping. All right? Piping needs to be braced depending on size. You know, you got a bunch of 1/2-inch pipes, obviously you don't. But then the US code keeps changing because what they'll do is they'll say, okay, if you hang a bunch of little pipes on a trapeze and it weighs more than 10 pounds a lineal foot, oh, then you got to brace that. And that was on for 2 cycles, and the newest cycle that just came out got rid of that. So we were talking about it before. The codes are like, you know, whoever votes this year didn't get enough votes next year, so that stuff that they put in 4 years ago was out this year, okay? Happens quite often, right? We were talking about for the CNBC, the same thing. Your codes have been going up and down and things have been changing. So you got basic 2 types of bracing that is used in the mechanical world. You've got cable bracing, which goes off both sides of whatever it is, and you've got a rigid brace, okay? You've got a rigid brace, okay? And what the difference is, this one you would typically use for something that is vibration isolated, and this one you could use when it's not isolated. You can use, man, what's going on here? You can use this if it's not isolated also, but you can't use a rigid brace when you've got vibration isolation because it'll deteriorate the vibration isolation. Okay? Now, the mechanical contractor has to get up to 2 places then to do the cable. All right? But it's a lot cheaper, so it's kind of, he's got to work out whether or not it's cheaper for him to get up to 2 places, all right, versus doing this, okay? Pipe ductility, all right, decides the performance of the piping system, all right? If you've got a glass pipe, that obviously is not going to be as strong as a welded steel pipe, all right? So in the US code, what we have is this RCP value, which is in the bottom of our code. So the higher the number in the bottom, the lower the force that you have to design for, okay? So if you've got a steel or welded pipe, right, the RCP is a 9, okay? So it cuts it down by 9. You take the steel and copper piping with threaded, bonded, compression, groove joints, right? And that's the big word there, the groove joint systems, okay? Building code says, oh, the RCP is 4.5. So you just double the value. If you had to design, if this was designed for 2,000 pounds, this one is now 4,000 pounds because it's a groove system. And then if you use cast iron, plastic, or glass piping, it goes down to a 3, so it's 3 times more load that you have to design for, right? These are just some things to think about in the back of your mind that, all right, maybe you might say, okay, well, it's cheaper to go this way, but then when you end up having to put in twice as many braces, it might not be. Okay? One of the problems that we ran into and we figured out in Northridge was what I call the pole vault effect. Okay? And what it basically is it says, I've got a rigid brace, and I've got a rod holding up this pipe, okay? And it's got an anchor up in here to the ceiling above. So what happens is, earthquakes go back and forth, and you'll see that in a few minutes with some of the photographs, right? Move in all directions, but we'll say, for this one, it's gonna move back and forth, left to right. Okay. When the load is going from the left to the right, what happens? The hard brace goes into tension, not a big deal, okay? The threaded rod goes into compression, not a big deal, okay? Everything seems to work. Now you come backwards, come this way now, come from the right to the left. So what happens? You come this way, this tries to go into compression, but guess what? It's rigid, it's not going anywhere. So this is the pole vault. This is the runner running, sticks the pole vault, and then this is his body going over. So what it does is it adds a vertical load to the rod that's holding up the pipe. And what did I just tell you about the anchors that hold up the rods? They're not covered under the seismic requirements. So this is usually an anchor that is not designed for anything other than the physical weight of this pipe. And now all of a sudden you've added seismic load to it. And we saw many failures of this. We didn't see them in the cable system because the cable system doesn't have that, right? But in the rigid system, we did run into those, okay? And with all bracing, one thing you got to look at is your hot water and your steam systems, all right? They are a brace, okay? You put these in and it will stop the pipe from moving. That's its basic idea, all right? So you have to work in conjunction with the mechanical engineer to make sure that you're not screwing up where he plans that pipe to move to during its lifetime. All right? You've got to work out the bracing so that he's happy and you're happy. Okay? And if you have a trapeze, it's basically the same thing. All right? Now the only thing different about a trapeze is you're going to put a U-bolt over the pipe so the pipes don't bang all over the place or try and jump off the trapeze. Okay? So if you got a cable system, like I said, if you went left or right, this is always going to be in tension, all right? And the cables are going to go, if it goes to the right, like it is, this one's going tension, and that one just gets slack. And then when it goes back the other way, This one becomes slack, and this one goes to tension, right? That's the way those work. They work out very well, okay? Now, longitudinal bracing, which is in the length of the pipe, right? If we were to use a system such as this on a longitudinal brace, which is really just, you're bracing the clevis hanger itself, okay? Because this little bit of movement within the clevis is not a problem. All right, transverse it, not a problem. In longitudinal, the pipe would just slide in and out of the clevis and wouldn't do you any good. So you actually have to brace the clevis. You have to brace the longitudinal brace with behind the clevis, and we usually use a pipe clamp. Put a pipe clamp on it, right behind it, and then you go off that pipe clamp. Now you're hooked onto the pipe itself. Now the pipe won't be sliding back and forth. Okay? Because this is what happens. Okay? Here's a pipe. Okay? Here's the clevis now. Here's where it used to be. Okay? That's about 6, 7, 8 inches. That's a fair amount of movement for an earthquake. Okay? So luckily in this one, it happened to have a vibration isolator at the top. So it was able to swivel around and do as it needed. Okay? This one here, this was a small trapeze that they had made. But as you can see, there was an insulation guard here, and it fell out somewhere, probably right at the very beginning after a couple of moves back and forth. But what I want to show you is this here. See all this scratching? That's the pipe sliding back and forth on that trapeze. All right? They could see 100 cycles back and forth on that pipe, moving back on top of that trapeze. All right? A lot of movement, all right, can be seen during an earthquake. All right? We also had a lot of pipe bracing that was called out, and we don't need to brace a lot of things. All right? There was when we started the ASHRAE section 2.7, it was actually it was TRG 2.7. That's when, before you become a technical committee, you are a TRG, which you're trying to become a TC. So what we were doing is working on trying to get a handbook chapter, all right? Because that's how you got to start. You got to start as a TRG, and you've got to put together a handbook chapter. Once you're in the handbook chapter, and everything goes well, you usually then can apply to become a TC, a full TC, okay? We had lots of contractors and lots of people tell us two different things. One, most pipes don't need to be braced. Let them just swing all over the place. Now, the Code of the United States says, if I have a pipe and it's less than 12 inches from the ceiling, and that movement is not going to impinge on anything else, we're going to let that swing. As long as the connection at the top can handle taking moments. And in other words, it's got to have some kind of swivel system, okay? So what happens here is, none of these are braced, and this thing here, swinging back and forth, just crushed the hell out of this duct, okay? All these pipes was probably swinging all over the place, okay? So here's a clevis, all right? Now, this clevis has got to be replaced. Now, the piping system obviously is up and probably still running, but this clevis is going to need to be replaced. Okay? What happened to this clevis? All right? The assumption is the pipe saw a vertical input, it went up, hit the center of the cross bolt, bent the bolt upwards, came back down, and then the rest of the clevis just slid down to its lowest point possible. Okay? This has got to be replaced. All right? And it's not easy to replace a clevis after it's been installed. All right? You basically got to go up there, you got to support this pipe, and then take this whole thing apart. Okay? Easy, cheap fix. All right? There are parts that you can buy from manufacturers to put over it to strengthen it. Put a piece of pipe. If that's a 3/4 bolt, take a 1-inch pipe. Cut it, stick it on here before this all starts, and you're never going to bend that. Because now you've got to bend a 1-inch pipe and a bolt, and you're not going to do that. You're not going to generate that big of a force, right? So what does it cost to have 6 inches of 1-inch pipe in there? It's going to cost you more for just the labor to cut it than anything else, right? But the amount of work that it's going to save after an earthquake, It's worth it, well worth it. So here's one of the, this is from SeaTac, all right, Seattle, Tacoma, all right. I was up there working and I was in the airport the day we had an earthquake. So what happens is, all of these pipes fell out, all of the sprinkler system fell out. And the reason they were all on C-clamps, right? Just C-clamped onto the side of a purlin. So what happens is, earthquake comes, it just pops off the side of the purlin. And now the whole system is down, okay? NFPA has now changed where all sprinkler pipe must now have a retaining strap, so it can't do that. And the US building code is just adding that in its last cycle finally, where you must have some form of retaining strap so that it doesn't pop off, okay? Duct bracing, all right? Same as mechanical piping, right? You need to brace certain sizes, all right? They can be either braced with rigid duct or they can be braced with cabling system, all right? So here's your basic ductwork system, all right? But a little different. So here you've got the duct, okay? What is duct made out of? Oh, we're gonna say 20 gauge sheet metal, okay? Can you put a 1/2-inch bolt through that and a big enough washer, you think, to keep that thing in place? Not gonna happen, okay? So what you end up having to do is you need to add some steel work, right? To hold that duct in place, and then you brace off the steel work, all right? Where you can get a positive attachment, okay? And then you sheet metal screw, all right? The steel work into the ductwork, so what you're basically making is a rigid frame so that this system stays in place. Now you're not doing this at every location. You're doing it at the seismic brace locations, which are typically every 40 feet, right? Every 13 meters, in that kind of neighborhood is where you're doing it, okay? If you do a rigid brace, it's the same thing, right? You're gonna have same steel work, you're gonna have sheet metal screws, and you're gonna have one rigid brace sticking out the side, okay? There is a National Association of Ductwork people, and I won't mention them. They fought us that ductwork does not need to be braced. Where can it go? It's not big enough. It doesn't have enough load on it, okay? Take a look at this. What you've got is a lot of straps. It looks like there used to be a piece of duct there. Oh, there it is. It's on the floor, okay? So what happened was, during the earthquake, these long straps just kept moving all over the place to the point where it pulled it out of here and then down it came, okay? That Sheet Metal Contract Association now has their own seismic manual, okay? They finally saw the light, okay? Suspended equipment, all right? Suspended equipment requires bracing depending on its size, all right? It can be, again, rigid bracing or cable bracing, all right? So the only thing that's different is, if I do a rigid brace, everything else that we did with a rigid brace, be it the ductwork or the piping, had one brace, okay? Can't do that with a piece of equipment, right? The reason we can do it with one brace on a piece of duct or a piece of mechanical piping is it's got length to it to keep it from being turned like this. You don't have that with a piece of mechanical equipment. You throw a fan up in the air here, and you put one brace on it, and that thing's just going to spin around that one brace like a top. Just going to go around in circles around it, okay? Even 2 braces isn't going to help you. It turns out you need 4 braces. So whether or not you go with cable systems or with a rigid brace, you're going to need 4 attachments for any piece of suspended equipment. All right, so cabling system, same thing. You put out 4 braces, okay? So here's a photograph of a fan that did very well during the earthquake. I took a few of these also just to show people that there was stuff that was done correctly, okay? So I've got this fan. It's got cable braces going out. Nothing happened to it during the earthquake. It swung back and forth, but stayed in place, okay? Floor-mounted equipment. okay? Has to be attached to the structure, all right? The equipment must be bolted to the structure and to the equipment itself, and it's got to be held in place by, if you can either bolt it in place if you don't have vibration isolation, or you need to have some kind of a snubber if you're going to use vibration isolation, which bypasses the vibration isolation, and for its day-to-day use, the seismic restraint is not in place, it's not in play, it doesn't work, and then as soon as the earthquake comes, it opens up, does whatever it has to do, and holds everything in place. Okay? Let's start with just floor-mounted equipment that's just hard bolted down. That's the easiest. Okay? So what we found at Northridge was, found a lot of bolts that were just sheared off. Right? And they weren't big pieces of equipment that should have, you know, it was such a big piece of equipment, and with the earthquake, man, it just took them off. It turned out they were small pieces of equipment, but what happened was, they went back and forth. Earthquakes, like I said, could have hundreds of cycles back and forth. So what happens is, you've got a bolt, and say you've got a pump you're putting down. You've got a bell and gasket pump, it's got 5/8 holes, you put 1/2-inch bolts in it, that's what you're supposed to do. And you pretty much center it as best as possible. Okay, now the earthquake comes. So what happens is, all right, so it moves to the right. So it smacks this side of the threaded rod, or the thread of the bolt. Now you got this gap, right? Builds up momentum, goes the other way. And now it smacks the other side. And it just keeps going back and forth, smacking that bolt till all of a sudden it fails. And this bolt head just breaks off. Right? 3 very easy little things to do to avoid this. One is you put a rubber grommet in there, all right, so it can't move back and forth. And what the rubber grommet will do is it'll actually de-accelerate the equipment as it starts to move. All right, that's the basis for all seismic snubbers, is having rubber inside of them so it de-accelerates equipment as it's trying to move. All right? You take epoxy compound, and I'm just talking about adhesive anchor compound. Squirt some of it in it, put the washer on it, bolt it down, you're done. Now you've filled up that gap, it can't bounce back and forth. Or you take the washer, and you tack weld the washer down. The average washer is a 1/64 of an inch bigger than the bolt that it's in, a 1/64 to a 32nd, somewhere in that area. So it can only move back and forth that small amount. Okay? 3 very easy, cheap fixes for saving equipment. Okay? But then you go to snubbers. So now you've got an air handling unit here, and we've got spring vibration isolators, and we need some kind of snubber to hold it in place. So what you've got is a snubber, and most of them are made, let's start with an angle. It starts with some form of an angle, and it's got some rubber bushings inside, and it's got bolts that go through. So the idea is you get it centered correctly, right? And then during the day, every day to day, while this thing's running, that bolt is in the center of that rubber washer, but it has an air gap around it. Usually between 3/16 to 1/4 of an inch of airspace. So that way you're sitting in it like this, and all day long it's fine. Now the earthquake comes. It hits one side, hits the other side, whatever. It can only move that 3/16 of an inch, and that's it. Right? And it holds it in place. Right? These are very effective snubbers. Work very well. Okay? Now here's a photograph I enjoy talking about. Right? This is a fan, one of 96 fans that fell down. Okay? And this structural engineer and everybody thought they had done the absolute best thing possible. Okay? What they did is when they were pouring the structural slab, they left pockets and they stuck rebar up, knowing that they were going to put these concrete walls up for the fans to sit on. They thought they did everything right. Okay? So what they did is they had these concrete walls about 2.5 to 3 feet high that the fans would sit on. Okay? And they even had seismic restraints on them, they had vibration isolators, all that. Fine. The problem was they only put up 2. They put one in the back and one in the front. So you stick this thing up 2.5, 3 feet in the air, and what have you done? All you've done is you've raised the moment on how much is the thing's going to move. All right? You have to brace these. All they needed was a piece of strut channel, on the decks, okay? Another $50 worth of mechanical, parts, and this thing never would have come down. And obviously 96 of them came down because they were all done exactly the same way, right? Without bracing, without some kind of bracing, all you're doing is you're raising the moment. That's all you do, right? Lifting it off the ground. Okay, this is another one of my favorites because this screams out, you need a flex connector on this piece of equipment. So here you've got this, heat exchanger, okay? So the earthquake comes, all right, you got it all hard mounted in, everything's just piped right in. So what happens? It rips off the end, okay? What do you got? You got 500 pounds of scrap metal. Okay? What else are you going to do with it? You're never going to find another end cap for that. Okay? So what are you going to do? You're going to throw this away. Hey, but what if you're a hospital and you need that? Okay? The thing to do is put a flex connector in here. All right? One of two things will happen. The flex connector will move enough so that nothing happens during the earthquake, or the flex connector fails. And then what happens? You put a spool piece in the next day, and the hospital's up and running again. Right? That's all you need to do. Right? Flex connectors can be a godsend. All right? And they can also be your biggest enemy. All right? The building codes require that you have X amount of movement based on the lateral drift between the two floors of wherever you are in the United States. So if you've got this floor to that floor, and this one's going to move an inch compared to this one, in the United States, you've got to have a minimum of an inch of movement. Okay? That means you've got to have a flex connector that can do that. All right? And then, so the first thing most people think, oh, I'll get some braided stainless steel hoses. Okay? Yeah, they'll work. They'll hold into it, but they won't move an inch. Braided stainless steel is the hardest of the flex connector series that you can buy. Unless you want a flex connector that's 3 foot long, it can't move an inch. You can see these little short ones. Oh yeah, you can move an inch. Yeah, it may be 500,000 pounds of force, but not what you're going to see here, so you never get the movement that you're looking for. Okay? This was that same hospital that had the housekeeping pad that shattered. This was the mechanical room in the 3rd sub-basement. Big difference. Nothing happened down here. Now, they had already come in and cleaned up all the water by the time I got to this portion. Okay? It has seismic restraints, vibration isolators. Basically, nothing happened down here in the third basement level. This is one of my favorite photographs for one reason. You got 2 chillers standing side by side. This is at the Academy Awards building. This is where they decide who gets the Academy Awards every year. Okay? So the system on the left, nothing happened to. The system on the right failed. The reason is, on the right side, all they did is they put 2 I-beams across, and they put snubbers and springs on it. Okay? The one on the left, they put 2 I-beams, but they put a channel between and welded it. They made it a 4-sided steel frame, rigid frame, and it stayed there. The mechanical on the right, he just went ahead and put in, like I said, 2 I-beams. So what happened is, equipment started to move, and it just rolled off the I-beam. Because the I-beam didn't have enough stability to stay in place. It just rolled over. Both systems were still running when I got there. The piping in this one the piping on the one on the left had pulled down about 2 inches, but the system was still up and running. This is one of my real pet peeves, okay? And that's why I chair ASHRAE's Standards Committee for testing of vibration ice for seismic restraints, okay? It's to get rid of junk like this in the field, all right? What you have is people selling unscrupulously, telling you anything you want to hear. Yes, this can handle the California hospital, no problem, okay? Any decent engineer worth his damn could take a look at this and say there's no way in hell, unless you're only putting 100 pounds on it, that it's ever going to hold up a chiller, all right? First, it's too tall. You got a little 1/4-inch plate on the bottom. You got one anchor bolt, because there's another one over there. You got one anchor bolt on each side. Just nothing there structurally, except for the channels. Hey, nice big channels. All right? Those are huge channels for something made as poorly as that. I'm surprised, okay? But basically, they shattered. And you don't want to be around when a spring breaks and goes flying. All right? They're deadly. All right? You hear about car mechanics trying to do a McPherson strut and the damn thing fly across the shop. That's exactly what happens here. You don't want to be around, okay? So ASHRAE has put together a standard, and I'll go over that in a minute. But that is, I chaired that for both cycles because I wanted to make sure to get rid of junk like this, okay? And junk like this. This is what we call OEM equipment, right? You buy a piece of equipment, oh yeah, we're going to give you the vibration isolation with it, no problem. And you get junk like this that don't even have a bolt hole. They put a little indentation for a slot on the end of the equipment, right? And it wasn't even bolted down, so this thing went all over the place. But what it also did is it brought up another problem. Look at the equipment itself. The equipment itself could not handle the seismic loadings. And that is another one of the new requirements in the United States. I'm going to show you some video of shaker table testing of equipment to pass to be able to be used in seismic zones. Okay? This I like to show because there was nothing on these. They had no seismic restraints. They had nothing. And they bounced around, but they stayed in place. And the only reason is these were so old, the springs were welded to the top and bottom plates. I don't think any manufacturer today welds the springs in place. We put them in castings and things like that. All right? Nobody does this anymore, but it was very interesting because it was so old, it worked. It stayed in place. It bounced around, but obviously it's about where it started, give or take an inch or two. This was, actually this photograph is from the '62 Alaska earthquake. I think it's '62, okay? What you basically had was the beginning of fragility levels of equipment. When should you start looking at the equipment itself, and when do you need to say, hey, that can't be used in this area because it isn't strong enough to be used for the seismic zone that we're in. So what you basically got here is a cooling tower, and as you can see, here's one of the lakes here, and it's just a piece of formed angle, all right? Don't know how thick it is, but wasn't thick enough in this corner. This one buckled, went down, and then the whole rest of the tower came down around it, okay? So ASHRAE has got method of test of seismic restraints, all right, for a method of testing for seismic rating and wind restraints. We keep changing the name, okay? So what this is basically a series of tests for things such as these here, all right? These vibration seismic restraint type of, when it does, that's it, okay? So those would undergo testing, and you basically would come out with a rating and say, hey, that's good for 1,000 pounds horizontally, it's good for 900 pounds vertically, whatever the number happens to be. But the testing gets done based on this test. This will end up in the U.S. Building Code in the 2024 cycle or something, I'm being told, okay? By then I'll probably change it again, but for now that's what it is. All right? And it's basically based on fatigue testing. If you've ever done fatigue testing for FM, it would be somewhat very much along the lines for an FM fatigue test. So here's, next I got is 3 videos. These are shaker table tests of 2 pieces of equipment for seismic certification for California hospitals. All right? This is an ASHRAE test. So what we did is ASHRAE, we wanted to see what was the best seismic restraint we could come up with. And there were 3 different things we were looking at. We were looking at how thick was the rubber, how hard was the rubber, and what was the air gap in the rubber. Remember I showed you this angle with that and so on? So what we did is we made up a mock seismic restraint, ran it through these tests, and Train and York were good enough to actually give us pieces of equipment to actually do the testing on, and we got the ratings for them at the same time. So they got something out of it, we got something out of it, okay? So, let's see how we get this to work. Where are you? Okay. So the way the testing is done is they do a quarter, what they call a quarter G, then they go half G, see, now it just failed because that door opened. I had to go back, they had to fix a latch. The latch had actually broken, they had to put a different latch on, and then they re-ran the test and it ran fine. So Train got this unit certified for California hospitals, all right? So what they do is you do a quarter of the roof load, then you do half, and then you do 3/4. So the idea is you do the full roof, which is the biggest loading possible. You do that last, so that if something goes wrong somewhere along the line, okay, we got as far as a half a G, we got halfway up the building, okay? All right, we're gonna have to make some pretty substantial modifications or whatever, but we're at least got a certification up to this level for now, and we'll come back in 6 months and we'll get the rest of it at that point. Okay, so that was how the system was worked. All right, so did one chiller, we did one air handling unit, and then we did this chiller. All right, let's see if we can get this to work again. Mind, yeah. Thank you, me trying to find it. So the University of Buffalo did all this testing for ASHRAE. All right, University of Buffalo is obviously not in a seismic zone. Okay, 15 years ago, when the U.S. government wanted to have another test lab, they put out for bids. So of course, all the West Coast universities put in bids. They wanted to have the government build this in their place. Government said, we got like 15 of them from the West Coast, nobody from the East Coast. Nope, gotta go out for bid again. And then they called Buffalo and said, guys, put a bid in. Buffalo put a bid in and got it instantaneously. Obviously everybody on the West Coast went crazy. Why are you giving it to people that don't have earthquakes? And the answer was, that is the reason why we're giving them. We're sick and tired of fixing your lab every time there's an earthquake. Okay? I've been getting Buffalo, we don't have to fix it. It'll last longer. Okay? So this is the testing that they do at Buffalo. Right? They have two. Now this is only one of two of the shaker tables. The other one is about 30 feet over to the right, and the two of them can be linked to be the biggest one in the United States. It might even be on North America, I'm not sure. Okay? And they can be run as one major, huge one together. Okay? Okay, last one. So this last one is a close-up of one of the vibration isolators on that chiller. Okay? So what you're seeing is everything moving up and down, and you can see the air gaps going through the air gap. So what I picked here to give you is I picked the one with the biggest air gaps, the smallest thickness, and the softest rubber, so everything would move the most. It's more dramatic that way, obviously. And this is what you would basically see in an earthquake if you were standing next to that piece of equipment and you had that size of an earthquake. Needless to say, you don't want to be in there servicing this unit when an earthquake comes, okay? You don't want to be there, okay? So this is basically what is being done, right? Testing of equipment to get what is known as a fragility level, so you can go ahead and say, hey, I can put this in a California commercial project up to this high in a building. I can put it up to a California hospital at this height, right, in a building, and so on and so forth, right? Being done, there are many shaker tables in the United States now. There are companies that are just making shaker tables because they see the future coming, okay? Then you've got some old ones, like the University of California at Berkeley. It's got one of the oldest shaker tables I've ever seen in my life. And they still do a fair amount of work. They've stopped doing research and they only do outside work now because they like the money, okay? Whereas Buffalo is stuck to, they can do 35%, and the other 65 has got to be research with the professors, okay? Okay, so here's the references. All right, the ASHRAE Practical Guide to Seismic Restraint. All right, the ASHRAE Handbook. All right, ASC 7 or 10, which is now 16, but most of the United States is not. They've not adopted the 16 yet, so I haven't put it in. And the International Building Code, which, all right, one of my things I talk about is everybody says, "Oh, I'm going to go buy the building code, so I know what I'm doing." And then they run out and they buy the building code. And then they get to the seismic section, and it's a paragraph long. And you go, wow, it should be longer than that. And that paragraph says, oh yeah, go buy this book. It's all in that book over there, right? So you spend $300 for this book, and then it says, oh, go buy this other book for $300. All right, so skip the bottom one, buy the top book. That's the real one, okay? If you work in the States, right? And then National Design Specification for Wood, all right? Best book on lag bolts I've ever seen. Okay. And that is it. Questions? Oh, come on, I'm not that good.
You mentioned about the technique of some contractors shortening the bolts.
Mm-hmm.
How would you know?
A couple of reasons.
After a point of failure.
Well, it wasn't a point of failure. In my inspections, I find them. All right. I had sent bolts that had to be embedded 11 inches. Right. And I had them made by a bolt company. So they're beautiful finished bolts. And when I got out there, the bolts were skewed. The tops were cut on angles. And I'm going, no, I saw the bolts before they left. They're all beautiful, nice bolts. And the guy goes, and he wasn't hiding it. Oh yeah, those were so long, I just cut them in half. You know, he wasn't hiding it. And I'm like, you know, now you just told me this, you have to start over, and we can't take these out. So now I've got to design something tonight, which you're going to put in tomorrow, and I'm going to come back the next day and inspect. You know, and he's like, oh, okay. He goes, but I'm not going to do it. I went, okay, this is a U.S. government facility. I'm going to go talk to the officer in charge of the construction. And next day he was, anything you want, I'll do.
Yeah.
You know, you want to keep going on a U.S. government project, you've got to do what they tell you. Yes, sir.
You mentioned York and Train.
I should have said that. You didn't hear me say that.
Yeah. Are there companies, are they certified? Do they have equipment that are certified?
For California hospitals and stuff?
Yeah.
Yes.
So they don't have to send their equipment to be tested?
No. It's not the way it works.
Okay.
All right. So what you have is, you have a model, okay? And you've got a 50-ton chiller, model CVHE, whatever. And it comes in a 30, 40, and a 50-ton, okay? What you do is you test the biggest and the smallest of that model series. And then if those two work out, they kind of grandfather the one in the middle in. But that's only that one series. So if you make 10 different types of chillers, you've got to have 10 different sets of chiller tests. All right? So in other words, you have air-cooled chillers. All right? They're obviously different than water-cooled. All right? And they're different than reciprocating chillers. So each one of those types, and then within it, you might have a CVHE, CVHA. Well, E and A, if there's a marketed difference, they got to be separately tested. So it ends up that you could have millions of dollars worth of tests, depending on how many different products you have. Or you might want to limit yourself and say, in California hospitals, I'm only going to offer these two, and that's it. All right? Which is the smart thing to do. Instead of trying to get your whole catalog done, you stick to a couple different types of equipment and say, for California hospitals or California certified, here's what you can select from.
Yeah, so you're saying that they do have some.
Oh, most manufacturers do. You know, if you go York train carrier, they all have something that they've already tested, right? Same thing with cooling towers, same thing with your pump manufacturers. They've all done some testing, right?
And so you're saying that these manufacturers have spent millions of dollars to do this testing and get certification on some of their equipment. So in other words, how expensive is it to build in California?
Well, it's not just California. I mean, using that certification, all right, they can use that in other parts of the United States, anywhere else that's a seismic zone. They can use that here in Ottawa, all right? It's not certified California. It's certified for a certain force level, okay? Which that force level could be anywhere in the world.
So are you seeing that everyone in California are using certified seismic equipment?
It's, in the US code, it's listed as the AHJ has the right to ask you for that documentation. In California, they just do it all the time. Other parts of the United States, it's hit or miss whether or not the local inspector knows what to ask for. But he can legally, in the United States, say, oh, that chiller you're planning on putting in my hospital in Memphis, I want to see documentation. And if he doesn't have it, he's out. He can be out.
So are they only looking at critical spaces?
No, it can be any AHJ for any project. So he can do it for a commercial project also.
Office building?
Yep, commercial project, he can ask for the same thing.
Don't be talking to any inspectors here.
I'm out of here at 7:30 tomorrow morning, don't worry.
Yeah.
Unless I can get a meeting before 7:30, I'm out of here.
No, because I have not seen any.
90% of the United States, we don't see it either, all right? Before I was talking to some people, I had an ASHRAE talk in Chattanooga last fall. And same thing, went over the same exact talk, and there was a building inspector sitting out there. And he came up to me after, he goes, am I supposed to be looking at stuff like this? And I basically said, yeah. And he called me up, and I came back to Chattanooga a month later, and I sat with the whole building department inspectors division and went over what had to be done. Whether or not any of them is doing it, I don't know.
And then you ran.
I went and had some chicken fried steak. Big Southern delicacy.
So what are you seeing down in the States in the form of, you talked right at the very beginning that it has to be part of the specification.
Right.
It has to be well documented.
Right.
Are they producing documentation, the consultants, whoever is producing the bid documentation, are they going to the extent of specifying and designing all of the seismic?
Oh, yeah. I see complete specs calling out that it must be a licensed professional engineer in the state of the location of the project, explaining what kind of documentation, what kind of calculations they're looking for. All right, there are complete specs out there. Even like Master Spec has one, you know, for a complete specification of what you need to do. Now the ASHRAE manual has this section. Now legally, we cannot call it a specification because then ASHRAE would be held liable. So it is called specification guidelines, okay, which keeps ASHRAE out of trouble. But it basically has most of the things that you're looking for to be put into a specification.
Yes, but then you're making it the requirement of the contractor to carry that engineer?
Yep.
Okay, so it's similar to what we do here.
Okay, 95% of that is not you hiring an outside engineer. 95% of it is the vibration isolation / seismic restraint vendor does the work, which is, like in my case, is me. My company manufactures the product and we design. You give us the drawings, we design everything, and then we certify it. So all he has to do is just hire us, right? There are local companies right here in Ottawa that does the same thing.
Yeah.
No, one of them has got a booth right there.
I was just curious whether you guys are doing the exact same thing what we're doing up here. We make it the responsibility of the contractor to follow the guidelines of the specification, to hire an engineer, a staffing engineer in Ontario actually, to do a seismic design of the installed product.
Basically, we go about it differently. The contractor hires the vibration isolation / seismic restraint vendor,
Okay.
and that vendor has his own engineering staff that designs everything and certifies it. So instead of going out and hiring an engineering company and saying, hey, do this, this, and this,
Yeah.
they hire a company like mine, and you get the engineering and the product as one. And
It is the same. I
Okay.
apologize. They generally do exactly what you're saying.
Okay.
So, yeah, that was my question.
Just on this, a clarification if we could. Right now we saw testing of an air handler, testing of a chiller, so those are major components, where really what we do here is we call up somebody for the restraint components, and the engineers let her recover those restraint components. So the object itself, cooling tower, chiller, boiler, whatever, it doesn't get tested for seismic here.
Well, we're missing that.
That's you're missing it.
We're missing the equipment.
Yeah.
Saying that the fan inside of a cooling tower is seismically okay, but the rest of the unit isn't, what good is that?
Yeah, I'm just,
Yeah.
this is the method we've got so far.
I came across this once when I was specifying air-cooled chiller, and I'd written that the equipment needed to be seismic restraint. I got the question from the supplier asking whether they wanted the equipment to be seismic design,
Yeah.
and that would be a hell of a premium that would have gone on to the equipment. At that point in time,
Yeah,
nothing in Ottawa.
10, 15 years ago, then it would have been done, a set of calculations by hand, and yes, it could have been very expensive. Whereas now, with the testing that they're doing, it's a series of tests. Yes, they're going to charge you more because they have X amount of money that they've outlaid, but it's a piece of paper that they already have that you don't have to wait 6 months for. It's, oh yeah, you want the seismic certified one? Here's the paperwork for it. And they go from there.
So long as it's one they've already tested.
I'm sorry?
So long as it's one of the series that they've already tested.
That's right.
Otherwise,
Yeah.
I forget, it was at least a 15,000 or 15% increase on the cost just to carry this one.
Okay.
But we're not seeing that here. I don't know if
No,
anyone else here.
I don't
has
see
seen
that.
it.
Like I said, I don't see it in most of the U.S. either yet. All right, I see it on the West Coast. I see it a little bit in Tennessee. Tennessee building officials are into it a little bit more than anybody else. And I see it in Missouri because they have the actual highest, in the United States, they have the highest capability for earthquakes, more than California does.
As a manufacturer who's undergone some seismic testing, I can say it's certainly becoming a lot more common. California was certainly the first place where we saw strong demand for this, especially with the code requirements on public buildings and whatnot. But a lot of it's spreading. A lot of other states start copying what California does, and in some provinces we see inspiration from their codes. It is becoming a lot more common.
Well, think about it from a building owner's perspective, okay? I can put a building up in California, and it costs me X amount, and this, and this. And I put a building up in Indiana, okay? How much more does it cost to seismically brace everything in that building? We'll say 1 or 2% on the total price of the building. Okay. I had a job in just outside Memphis, Tennessee. It was a large, one of the big sneaker manufacturers. He wanted to build the biggest warehouse in the world with sneakers, so he could have them all made, and when they want to ship out, they can ship, 1,000 sneakers a second, kind of thing. So they decided to build just outside Memphis. And they actually went outside Shelby County. Memphis is in Shelby County, and they're seismic. The county next to them was not seismic. So they built over there, not specifically like we went over there to scoop the seismic. It was just where they bought their land. So they get all done, they build this big, beautiful building, and the insurance company comes in. And they're looking, where's your seismic? We're not in that area. 3 blocks over, you know, Shelby County ends 3 blocks over this thing. And he goes, oh, okay, I understand that. He goes, let me tell you something. He goes, here's your premium now.
Yeah.
Here's your premium if you get seismic restraints put in after the fact. It was like a 2-year payback, okay? Needless to say, they've done it. And there's been a lot of jobs like that being done after the fact, just because they get that first bill and they go, oh my God, I didn't think it would be that expensive. But it turns out you stick $150,000, $200,000 worth of equipment in, and all of a sudden your bill drops a quarter, you know, and that's what they were looking for, you know. The insurance industry is one of the people driving a lot of the seismic restraint work, right? They would rather you spend a little money up front and them not have to pay you back a big amount later on. Any other questions? Yes, sir.
This is maybe harping on the same thing, but bear with me. Like here we have facilities called post-disaster facilities.
Mm-hmm.
Fire station.
Right. Hospitals, police stations, things along that line.
Would the California or some of the codes you see, would they be along that lines? Because you mentioned a product tested for a hospital application. So it's
Yeah, that's the same. Post-disaster in California is hospital, police, and same thing. All those must have them in California. Whereas commercial building doesn't have to, but the AHJ can request it. So you have to be nice to your AHJs if you're on a commercial project.
Yeah, one of the good things on that, you do being tested, there's going to be 2 main levels. One is that the equipment survives intact, it doesn't necessarily have to work. The other is that it survives and continues to work in a mission critical facility. You have to do that.
And a lot of companies are going to mission critical just because they look at it and they go, hey, like you take a lot of like, we'll say Verizon and companies like that. If their servers go down because they have no electricity, they're out millions of dollars a minute, okay? So if they put in $100,000 or $150,000 worth of seismic restraints at the beginning of building a building, it is nothing compared to what it's going to cost them for the time that they're shut down. And that's how a lot of companies are starting to look at it that way, and a lot of insurance companies are kind of telling them in advance, we think you should do this, here's why, and they're telling them the reasons. No other questions? Let's have a beer.
Well, before you head off here, I just wanted to present you a coin from the Mint locally, a gift and a thank you for speaking to our chapter.
Not a problem. Thank you so much.
Well, thank you very much for coming and doing this for us, and hope you have a good flight back. Just wanted to close by saying you should get an email with an evaluation form. It'll be the distinguished lecturer form, so if we can get some feedback on how you found the meeting, what you'd like to see in the future would be great. Next meeting will be back here in March, and if you have time, if you're looking at career fair or ASHRAE curling, make sure you go on there and register. I think the deadlines are coming up. So if there's nothing else, we'll see you all at the next meeting in March, and thank you very much. Have a good night.